Have you ever just sat and stared at a candle flame? Or a campfire? So, what is it? If I asked you to classify everything in this room, you could probably do it easily. This table is a solid. The water in your glass is a liquid. The air you are breathing is a gas. But what about fire? It has a shape, but you can pass your hand through it. It gives off light, but it's not a light bulb. It feels like wind, but it burns. Is it a gas? Is it a liquid? Is it a solid? Actually, the answer is none of them. Fire isn't a thing at all. Fire is a happening. It is a chemical reaction happening so fast and so violently that it creates its own light. Let's break it down. Chapter 1. The recipe, the fire triangle. To understand fire, we first need to look at the recipe. In school, you might have heard of the fire triangle. It's the three things you need to make a fire exist. Fuel, like wood, wax, or gasoline. Oxygen, from the air. Heat, to start the reaction. If you take away any one of these, the fire dies instantly. If you pour water on a fire, you remove the heat. Fire dies. If you cover a candle with a glass jar, you remove the oxygen. Fire dies. And if the wood burns up completely, you have no fuel. Fire dies. But here is the part most people miss. The fuel, the wood or the wax, doesn't actually burn. Wait, what? Yes. If you hold a match to a thick log, it won't catch fire immediately. Why? Because the solid wood can't burn. The heat has to turn the solid wood into a gas first. When wood gets hot, it releases volatile gases. Those gases mix with oxygen, and that is what ignites. So when you see a log burning, you are actually watching gas burning just millimeters above the wood. Chapter 2. The chemistry. Now let's zoom in. I mean really zoom in, to the atomic level. What is happening chemically? Let's look at a candle. Candle wax is a hydrocarbon. That's just a fancy word meaning it's made of long chains of hydrogen and carbon atoms holding hands. Then you have the air, which is full of oxygen, O2. Usually the oxygen and the wax ignore each other, but when you add heat, chaos happens. The heat makes the atoms vibrate like crazy. The chains of hydrogen and carbon break apart. They are now looking for new partners. The oxygen snaps them up instantly. The carbon grabs the oxygen to make carbon dioxide, CO2. The hydrogen grabs the oxygen to make water, H2O. Remember the rocket video? We talked about how H2 plus O2 makes water. The exact same thing happens in a candle flame. This bond swapping releases a massive amount of energy. That energy is the heat you feel. So simply put, fire is the rapid shuffling of atoms from a high energy state, wax, to a low energy state, CO2 and water. Chapter 3. The color. Why is fire blue and yellow? But if fire is just invisible gases turning into other invisible gases, CO2 and steam, why can we see it? Why is it bright? This is where it gets interesting. Look closely at a candle flame. You will see two main colors. At the very bottom, it is blue. At the top, it is yellow or orange. These two colors come from two completely different physics phenomena. The blue part at the bottom is where the combustion is perfect. There's plenty of oxygen, so the fuel burns cleanly. The blue light comes from the molecules themselves, specifically carbon and hydrogen, vibrating and shedding energy as light. This is called chemiluminescence. It's the same reason a gas stove is blue. It's clean, hot, and efficient. But as you go up the flame, the oxygen runs out. The fire can't find enough oxygen to burn all the carbon. So some of that carbon gets left behind. It forms tiny microscopic specks of soot. These little specks of solid carbon get carried up by the heat. They get hot, really, really hot. And when things get hot, they glow. This is called incandescence. It's the same way an old-school light bulb works, a hot wire glowing yellow. So the yellow part of the flame isn't a chemical reaction. It is basically thousands of tiny glowing rocks floating in the air. Chapter 4. Pollution. The cost of dirty fire. This leads us directly to pollution. Remember how I said the yellow part is unburned carbon? Well, if the flame is working perfectly, everything turns into invisible CO2 and water. But fire is rarely perfect. In a forest fire, or a car engine, or a coal plant, there isn't always enough oxygen to go around. The reaction gets messy. Instead of nice, clean CO2, you get carbon monoxide, which is a deadly poison because it only grabbed one oxygen instead of two, and you get that black soot, the unburned carbon we talked about. And when that soot cools down, it turns from glowing yellow to black smoke. So smoke is just wasted fuel. It's carbon that didn't get the chance to burn. This is why modern cars and factories have filters and catalytic converters to try and finish the job that the fire missed, turning that dangerous pollution into safer gases before it hits the air. Chapter 5. The Carbon Cycle. Fire is sunlight. Now I want to leave you with a thought that changes how you see fire forever. We know what fire is now, but where did the energy come from? Let's trace it back. You burn a piece of wood. Where did the wood get the energy to grow? From the tree. Where did the tree get the energy? From photosynthesis. The tree took carbon dioxide from the air and used sunlight to split it apart, keeping the carbon to build its trunk and releasing the oxygen for us to breathe. So a tree is basically a battery. It stores sunlight in the form of carbon wood. When you burn that wood, you're actually running the movie in reverse. You're taking the carbon, adding the oxygen back in, and releasing that stored energy. The heat you feel from a campfire? That is sunlight that hit the earth decades ago. The light you see from a candle is ancient solar energy released all at once. This is the carbon cycle. The plant breathes in CO2 to grow. The fire burns the plant and releases the CO2 back into the air. Then a new plant breathes that CO2 in to grow again. It's a perfect loop. Life, death, and rebirth, powered by the sun. The problem we have today is we're digging up fossil fuels, ancient plants from millions of years ago, and burning them all at once. We're overloading the cycle. But the chemistry? It's exactly the same. So, the next time you strike a match, remember, you're not just making heat, you are making a chain reaction of atoms. You're witnessing the physics of glowing soot, and you're releasing sunlight that was trapped in a battery made of wood. It's not magic, it's chemistry, but it's still pretty magical. If you want to know more about how the world works, or if you have a topic you want me to cover, maybe electricity or how nuclear reactors work, let me know in the comments. You can subscribe if you learn something new.